Hello everyone, today I am going to present the real-time EV monitoring and ADAS dashboard project internship at Emertxe Technologies. My name is Lokesh and I am from ECE Meenakshi College of Engineering. Introduction. The rapid transition towards electric mobility demands advanced interface that unify performance metrics with driver safety layers. This project addresses that need by engineering a real-time EV monitoring and ADAS dashboard system that leverages an STM32 Blue Pill microcontroller to stream critical velocity, battery, and 3-axis ultrasonic radar data over a high-speed UART connection to responsive 10 Hz Python Matplotlib digital instrument cluster. And the project objective. First, primary objective. Here, design and simulate a real-time EV telemetry acquisition board and ADAS ecosystem capable of processing environmental hazard and powertrain metrics. Next, on-chip modeling. Implement physics dynamics models for acceleration, braking, and battery shock and the MCU. Next, ultrasonic radar grid. Here, engineered a 3-axis ultrasonic array to provide front collision warning and blind spot detection partial warning. And finally, the telemetry and UI. Streams multi-variable data with a low latency serial protocol to a responsive Python Matplotlib instrument cluster. And the hardware and software stack. Here we are using MCU as STM32F103C8T6 microcontroller called Blue Pill. It works on 8 MHz base and 12-bit ADC converter includes sensors, multi-channel analog potentiometer for throttle control, brake and temperature changing, and 3-axis ultrasonic proximity grid for finding front, right and left. Activators are used is for diagnostic LEDs and pulse width modulation buzzer for tired auditory alert, and firmware and tools STM Cube IDE and PICSimLab for hardware simulation. Host and visualization we are using Python and VSPE tool for visual communication. And the operational parameters we are using is first sampling and 12-bit ADC quantization and UART at 1,15,200 bps telemetry frame emitry every 100 milliseconds, and a drive envelope velocity 0 to 200 km/h and a motor torque up to 250 nanometer. Configurable drive profile as eco, normal and sport, and ADAS threshold for front collision warning advisory less than 50 centimeter and the critical is 20 centimeter, or blind spot detection triggers within 30 centimeter when speed greater than 20 km/h, and the thermal fault alerts greater than 80 degrees Celsius in the engine. This is the workflow of our project. First, the input side we are using sensor with the potentiometer used for acceleration control and brake control, temperature and state of charge. And we are using ultrasonic sensor for finding the collision distance. And next, the STM32 Blue Pill used for EV control ADAS and the engine fault handler. And the UART we are using telemetry frames, and the Python dashboard where a speedometer and shock bar ADAS bird eye has been visible. And the outcomes validation and key results. Hardware software integration proved an ARM Cortex M3 microcontroller can compute concurrent vehicle physics and multi-axis ADAS radar tracking without process blocking. Next, low latency telemetry loop established a reliable 1,15,000 to 200 bps UART pipeline, achieving a clean 10 Hz dashboard refresh rate with zero interface lag. Next, file safe mitigation. Build an 8-bit diagnostic fault register that instantly intercepts vehicle operation, dropping torque to zero and triggering immediate driver alert during safety failures. Results summary and validation test. Dynamic speedometer matches simulator throttle input and battery shock depletion. Brake input greater than 5% engage negative torque and regenerative charge event in real time. And the front collision warning and the blind spot detection routine reliably escalated As advisory at less than 50 centimeter, critical at 20 centimeter with Python UI color state and hardware buzzer confirmation. Thermal interlock test. Motor temperature greater than 80 degrees Celsius. Set fault 0 torque output and asserted fault LED instantly verifying protective control loop. Next we are moving to the programming part. Here it is the STM32 cube IDE. Here we first configure the IOC file for our project. In this IOC file we are using the STM32 F103C8T6 microcontroller, and we are configure all the pins, analog pins, timers and connective pins. Next, after saving, we generate the programming for this microcontroller. Here is the all codes we used in our project: main.c, uart.shell, uart shell.h, fault.c, ADAS, EV controller.c, everything. After successfully compiling the program without error, we generate the bin file for our project and opening the PICSimLab for showing the output. Next, we are opening the PICSimLab. Here we are choosing the microcontroller that we use in our project. Here we open the bin file that we compiled in the STM32 cube IDE, and we add the spare parts for our project. In these spare parts, we are using ultrasonic sensors and potentiometer and LED indicators. We are using 4 potentiometer for 4 analog inputs and ultrasonic for finding the distance of collision. And the visible terminal shows the output of our project. Here we are seeing the speed of our car and the state of charge and torque, temperature of our battery and the range of battery, and the acceleration level, brake level, and the front collision distance, left collision distance, and the right blind spot distance, and we are showing the time to collision and blind spot and alarm and fault. After successfully connecting all the spare parts in PICSimLab, we are opening the VSPE tool, where we are connecting the ports as COM1 and COM3 virtually. It helps to connect the simulation software to connect and sharing the data virtually. Next, we are opening the command prompt, where we are opening the file of Python dashboard where we have saved our file. Here we are opening the Python file as a Python, the file name and /port comp3. After opening the Python dash, where we see our working project. Here it shows the distance of first front collision warning as 340 centimeter. If I reduce the front as below 150, it shows warning when the car is moving and the car is stopped. After no critical level is showed, the car started to move. If I here we see the car speed is increasing when I applying the accelerator. If I increasing I, the speed is increase more, and I applying the brake for the reducing the speed and reduce the acceleration. And I reduce the brake and applying the speed again. The battery level is reducing gradually. The maximum speed is 200 km per hour for our car. And here it shows the torque of our car and the acceleration percentage, brake percentage, and the temperature of our battery motor. And I am reducing the car speed and increasing the temperature. First I increasing the brake for reduce the car speed. And we wait for below 100. The car will move slowly at the current rate. And I am applying the temperature change in the motor. The temperature change will shows as fault when it reaches 80 percentage. Above 80 it shows as fault. Here the temperature of the motor shows here. And the collision we find it shows us alert in the sensors and also AB monitor. And blind spot detection, I'm reducing the left below 20 centimeters. It shows us advisory, and the car has been getting slow. And I am also reducing the distance of the right BST, and it also shows us advisory alarm. And if there is no advisory or alarm, the car started to move. You can check. This is my project, and thanks to Emertxe for help me to complete this project. Thank you.